with K8 scheduling.
Yeah, can you hear me, Alessandra? Cool. I'll go to the first slide then. Okay, you can see the slides?
Yeah.
Cool. Okay, so I'll continue the same subject, and I'll talk about GPUs, but in the context of the integration we've done at CERN for Kubernetes and also OpenStack. So what we've tried so far, we had some NVIDIA K20s and also some Vega cards from AMD, some that we are not using so much anymore. Mostly we moved to enterprise cards. We also had some 1080s and 1080 Ti's, but we moved to using only enterprise cards and mostly from NVIDIA. And the reason is license, as probably everyone knows about this already. So we have a few P100s and more V100s and soon T4s. We started looking at the differences of over these cards also. So V100s, they have more memory and more cores, but actually T4s also have a good use case as they are very low power consumption, something like 70 watts, while V100 will go to 50 or even 300. They also have passive cooling, which is interesting. The reason is that we can probably have much higher density per node using T4s than with a V100. Integrating GPUs. So there are different ways that GPUs can be integrated in the infrastructure. So the first option is to just provide bare metal nodes to the end users, and this is pretty straightforward. The device will just be present. If we provide using virtual machines that we want to do for multiple reasons, there's two ways. We can either do PCI pass-through, where we just expose the full device directly to the virtual machine, and the virtual machine sees it as if it would be in a bare metal node. Or we can do vGPUs, where the GPU is partitioned into multiple slots, and then each of this partition is exposed to the virtual machine, and there's some kind of independent in the isolation sort of done by the driver. We currently offer both bare metal and PCI pass-through, but we are pretty advanced also to offering vGPUs. There's also use cases for all of them. The use case for vGPUs is twofold. One is to provide proper monitoring, and I'll talk about this in a bit, to the infrastructure, from the infrastructure. Doug was also mentioning that we need to see how the GPUs are being used, and if we just do PCI pass-through, we actually don't have this visibility in the infrastructure. And the other one is that a lot of workloads we've seen are pretty spiky, and the usage of the GPU varies a lot during the day. So it would be interesting for these workloads that don't need a lot of the GPU all the time, that we could kind of overcommit a bit, like we do with CPUs already. Because at CERN we have a cloud based on OpenStack, this is how we did integration. So I made a table here with kind of different criteria, but basically, like for scheduling, the proper way to do it would be with vGPUs. Right now we have to play a bit with flavors, but it's okay, we can do it. Quotas we can't provide with OpenStack right now for PCI pass-through and bare metal, but actually we can with vGPUs, so that's also why we are investing a bit. Monitoring, as I mentioned, so if we do vGPUs, we can actually have monitoring vision from the infrastructure. We can see how the virtual machines are using the GPU. If we do PCI pass-through, because we pass directly the device to the node, we cannot do this from the hypervisor. So this is also an interesting part of vGPUs. The sharing GPUs, so there's a few use cases for this. It's not the main one, but if we want to provide this, we would need vGPUs. And then one very interesting one is NUMA topologies and affinities. There was some talk already earlier about this. If there's a lot of chat between the GPU and the CPU, we better make sure that they are in the same NUMA node so that this is efficient. In OpenStack, this is still not possible today with the vGPUs. It is possible with the other two options. And then we are evaluating the performance a bit, but we know that there's a loss if we use vGPUs. We're just not sure yet how much. And then for the license, so there's no special license if we just do PCI pass-through or bare metal, but actually if we want to do vGPUs, you need to pay for a subscription for vCompute server in NVIDIA, and the price is around $50 a year, and you can do up to 8 VMs per GPU. This is one of the options of this grid licenses. So for us, if we want to offer GPUs as first class like we do CPUs in OpenStack, the easiest path seems to be vGPUs. We just have to make sure that we don't lose too much. In the end, we probably will be offering a mix of PCI pass-through and vGPUs as well. Also, this way of doing quotas for vGPUs wouldn't work for other type of accelerators like FPGAs, because it's really dedicated to GPUs. So we will still need PCI pass-through for those. And then coming to Kubernetes, so the way we do we deploy our Kubernetes clusters is that all of them are backed up by OpenStack nodes, can be VMs or bare metal. Then we have a way to provide heterogeneous clusters by having node groups, and each node group can have specific characteristics. In this case, it's mostly the flavor that is interesting, as we can have node groups that have CPUs in different availability zones, but we can also actually have in the same cluster one more node group that has GPU backed nodes. The configuration of the GPUs in Kubernetes is pretty straightforward. We developed a Helm chart that does the detection and the configuration of the GPUs automatically, so the users don't have to care about this. It just the GPUs just show up available in the Kubernetes cluster, and NVIDIA has developed a GPU operator recently that is doing basically the same. They both rely on a device plugin for Kubernetes. There used to be a way to do NVIDIA Docker, which is a Docker release that NVIDIA was maintaining, but this is not required for Kubernetes. We can do plain containerd or whatever container runtime you decide to use, and then use the device plugin to configure the GPUs and make them available in Kubernetes. So the same table for Kubernetes looks a bit better. The main reason for this is that there's a big push in the Kubernetes community to integrate well with machine learning workloads, tools like Kubeflow, and more recently Torch Elastic for PyTorch specific distributed workloads. So all this functionality is there apart from sharing. So it's not possible today to do fractions of GPUs in Kubernetes, but all the rest is very well integrated. So it's pretty easy to deploy your workloads on a Kubernetes cluster if you want GPUs. I put an example here. All you have to do is specify the resources that you need one or more GPUs, and it will schedule to the node that has these resources available. If you use the NVIDIA, there's also a way with the monitoring. Oh. Hello, can you hear me?
Yes, but I don't see anything anymore.
I don't see either.
I actually see the mouse moving.
It's somebody tried to annotate the thing. This is what we were struggling with before.
It was
Okay,
me.
this is the first time that, okay, seems to be back now. I have no idea what happened. It's the first time that this happened to me.
Ardo, I had to stop your sharing so you can restart it and then it should display well again.
Can you see it again?
Yeah, now it's working. Now it's back.
It's coming back.
Okay, it's the first time that this happened to me.
But we do see two black rectangles,
Yeah.
Okay.
right? One on the top of the screen and one on the right. Yeah.
Okay, I'll move them out. The top one, I don't think I can move right now. I'll just continue.
The one on the right was more annoying.
I can imagine. Okay, I'll just finish off. So the allocation is pretty easy. You just specify the amount of GPUs you need, and then it will do the scheduling. The GPUs are exposed, and if you list the nodes, you see that they have a special role that says they have GPUs. The monitoring is quite important. So we already heard this in the previous talk. So there's a Prometheus exporter for GPUs from NVIDIA, developed by NVIDIA, maintained by them. They also provide all the Grafana dashboards that are required, and you can see a lot of metrics like temperature for both memory and the GPU. You can see the clocks and power usage, throughput if you're using PCIe or NVLink. I leave the link here. In our clusters, we just deploy this by default, so all the end users get this monitoring for their nodes, and we also get it for the clusters we maintain. Yeah, so next steps, we want to finish evaluating this performance penalty for vGPUs, as there is this use case for spiky workloads where this could be interesting. So it's probably the case that we'll end up offering both PCI pass-through and vGPUs. There's something very interesting with this NUMA affinity. It's pretty clear that if you don't have CPUs and GPUs sharing the same or in the same NUMA node, you will see a big drop. So we want to explore something that is called topology manager in Kubernetes. That is a pretty advanced way of expressing these NUMA affinities. And then we saw in the previous talk also that there's AMD and Intel that are betting on GPUs for the near future. So if we want to do vGPUs for this kind of cards as well, the technology used by NVIDIA is proprietary, so we would have to use something like SRIOV, which is very popular for network acceleration, but also works for other accelerators like GPUs. We don't have any, because the talk was Kubernetes and heterogeneous resources, we actually don't have any requests right now to integrate other types of accelerators in Kubernetes. Things like FPGAs. We also don't have a lot of FPGAs as far as I know in the data centers. So we do get occasional requests to integrate like special devices, tape drives and special dongles. So we could look into this, and things like NUMA affinity work very well also if you use this kind of thing. And that's all I have.
Okay, thanks.